Think about it. Concrete is literally everywhere. It builds our entire world. But have you ever stopped to wonder what's really inside it? Well, in this explainer, we're going to pull back the curtain on the secret ingredients and the incredible chemistry that lets us build everything from our sidewalks to soaring skyscrapers. Let's get right into it.
Okay, let's start with a question that gets right to the heart of the matter. It seems like a total paradox, right? How is it possible for engineers to pour a mind-boggling amount of concrete for a dam in the blazing summer heat, but a simple patio in your backyard can completely fail in the cold? Well, the solution isn't about the big things you already know. The cement, the water, the rocks. No, it's about something much, much smaller. We're talking about materials added in incredibly small, precise amounts. And this, right here, is the magic of modern material science. These tiny little additions give engineers an unbelievable level of control, transforming a basic mix into a custom-built high-performance material. So what are these secret ingredients actually called? They're known as admixtures. The best way to think of them is as performance-enhancing additives for concrete. They're not part of the basic recipe, but man, do they fundamentally change how the concrete behaves. Now, these admixtures basically break down into two main families, and once you understand the difference between these two, you'll see how engineers can cook up the perfect concrete for pretty much any job on the planet. Okay, so here's the breakdown. On one side, you've got chemical admixtures. Think of these as your tactical specialists. You add just a tiny bit to solve immediate problems right now, like controlling how fast it sets. Then, on the other side, you have mineral admixtures. These are the long-game players. You add them in bigger amounts, and their job is to build strength and durability for decades to come. So first up, let's tackle two of the biggest headaches on any construction site: managing the clock and making the concrete actually flow where it needs to go. You got to imagine this. It's a huge logistical nightmare. Concrete hardens because of a chemical reaction. If it's hot outside, that reaction goes into overdrive, and your concrete might get hard before you can even finish placing it. But if it's cold, the whole thing grinds to a halt, messing up your entire schedule. So how do you take back control? The solutions are actually pretty intuitive. It's like having a brake pedal and a gas pedal for that chemical reaction. The brakes are called retarders. They slow everything down, which is absolutely essential in hot weather. The gas pedal? Those are accelerators. They kick the reaction into high gear, which you desperately need when it's cold outside, so the concrete can get strong fast. But here's the catch. When you're messing with chemistry, there are always risks. For instance, the most common type of accelerator works great, but it contains chlorides that can actually attack the steel rebar inside the concrete, causing it to rust. That's a massive problem for long-term safety. And if you add too much retarder on a cool day, the surface can stay wet for too long and start to crack. You have to be incredibly precise. Okay, so controlling time is one thing, but you also have to make the concrete flow properly to get it into all the nooks and crannies of the formwork. Now, the easy fix is to just add more water, but that's a terrible idea. More water means weaker concrete, period. So the real challenge is to make it flowy without adding more water. And that's where water reducers come in. These chemicals are amazing. They basically make the cement particles slippery so they slide past each other more easily. Your standard ones, called plasticizers, can cut the water you need by about 5 to 10%. But then you have their big brothers, the Superplasticizers. And these things are a total game changer. I mean, just look at that number. Slashing the water needed by up to 30%. That's incredible. And it gives engineers two superpowers. They can either make concrete that's way, way stronger, or they can create self-consolidating concrete that flows like water, filling up the most complicated forms all by itself. So we've gotten the concrete in place, it's set on time, it flowed perfectly. But now for the real test, making sure it lasts for a very long time. This is all about building for ultimate durability. This is where we get into the real fight against the elements. Because concrete might look tough, but on a microscopic level, it has enemies. Water can seep in, freeze, and literally tear it apart from the inside out. Chemicals in the ground can eat away at it. The steel inside can rust. How do you fight all of that? Well, the first line of defense is just pure genius. It's called an Air-Entraining admixture. It's basically a special kind of soap that whips billions and billions of tiny, stable air bubbles into the mix. So when water inside the concrete freezes and expands, instead of cracking the concrete, it just squeezes into one of these little air pockets. It's like building millions of tiny expansion joints right into the material itself. And that leads to this really powerful and honestly kind of counterintuitive idea. For concrete that's exposed to the weather, like a sidewalk or a bridge, having the right amount of air inside for protection is often way more important for its long-term survival than its raw strength. Okay, so we've defended against the physical attack of freezing water. Now let's talk about chemically upgrading the concrete itself. For that, we turn back to those mineral admixtures we mentioned earlier, also known as SCMs. These are often byproducts from other industries that can make the concrete fundamentally better. The magic here is something called the pozzolanic reaction. Here's the simple version. When cement and water mix, they create the strong glue that holds concrete together. But they also create a weak, chalky byproduct. Well, what these SCMs do is they hunt down that weak byproduct and chemically react with it, turning it into more of the strong glue. It's literally an internal recycling program that makes the concrete stronger and denser. How cool is that? And what's great is that different SCMs are like different tools for different jobs. You've got fly ash, which comes from coal plants. It's great for massive concrete pours because it keeps them from getting too hot. You've got slag from steel mills, which is fantastic at resisting chemical attacks. And then there's silica fume. This stuff is an ultra-fine powder that plugs up all the tiny holes, creating incredibly strong and impermeable concrete. Okay, so we have all these amazing different ingredients, the gas pedals, the air bubbles, the chemical recyclers. How do engineers actually put all the pieces together to create the perfect mix for the job?
Well, the big takeaway here is that modern concrete is almost never simple. High-performance mixes are all about creating a team of admixtures that work together. For instance, they might use what's called a ternary blend, where they combine cement with, say, silica fume for that early pop of strength, and fly ash to give it durability for the next 100 years. It's all about synergy.
And this is a huge but. With all this amazing power comes a huge amount of risk. This is not like cooking where a little extra flour doesn't matter. You get the dosage wrong here, and the results can be a complete disaster. Too much superplasticizer, and your concrete just separates into a pile of rocks and water. Too much air, and your strength plummets. It really shows you this is a very precise science. And that's our deep dive into admixtures. So really, the next time you're crossing a bridge or you see a skyscraper or reaching for the clouds, remember what you saw here. It's not just a lump of stone. It's a sophisticated, high-tech composite material, packed with an entire cocktail of hidden ingredients, all working together to make it strong and durable. So ask yourself, what secret ingredients are hiding inside? Now you know.